And there is an amazing hands-on exercise this afternoon, a lab exercise, and I highly recommend anyone who wants to really learn about transformers, listen to the slides, to the presentation, but then make sure you do that collab. Because if you do both, I think you just walk out of here knowing transformers well. I'm going to describe transformers, and then I'll try to also discuss how transformers are used. And really, it's one of the key building blocks. If you know about transformers, you'll understand, I think, 60% of the papers that come out. So there is this hypothesis, which is becoming much more widely accepted these days, and is that everything you know, your memories, the knowledge of who you love, your hopes, your fears, and all get encoded in a neural network in your body. Most of it is in your brain. And for the last 80 years, scientists have tried to recreate these with machines. So they built models of neurons. They learned from neuroscience that neurons fire for particular patterns in the world. Like there was a beautiful experiment in the 50s by Hubel and Wiesel, who would show a cat an edge on the screen, and then they would rotate. And depending on the angle, different neurons in the visual cortex at the back would fire. And so they knew that, okay, so this is how brains represent the world. Neurons fire for specific patterns. And then if you have several layers of these, or several stages, these neurons become more and more complex, and they start firing for different things. Some neurons will fire for when you see, I don't know, your husband, for example. Or as we see in this animation, you can show a cat to the to one of these artificial neural networks. The cat goes through these neurons, and then, or a dog in this case, and then the network will output a symbol, in this case the word dog, and if what the network outputs is right, matches the input, then the network stays the same. And the way we teach these things is if it doesn't predict the right thing, then we change the weights. We adjust all the neurons, all the strengths of the inputs, or what we call synaptic weights, until the network predicts the right thing. The way we do that is using an algorithm called backpropagation, which is just gradient descent, just standard vector calculus. And these days, no one even needs to know what that is, because there's packages like PyTorch and JAX and so on that just essentially implement. They basically, their purpose is to implement that algorithm. So instead of talking about the algorithm, I'm going to focus more on the explaining the architecture. And of course, we can do this for images, but we can also do this for text. If we have a sequence of words, like here, the wheels on the bus go. Okay, most of you, so it seems to be an international song now. Effectively, they go round and round. So you predict the next word. And in order to predict the next word, for any possible start, the network has to compress that input signal. It has to learn. There's no way it can succeed unless it learns what's the structure in those sentences. It has to learn an abstraction, just like you learn all these features of ages and how to compose ages to be able to understand what a cat or a dog is. Here you need to understand what the structure is of language to be able to predict the next word. And extracting the structure is something that I like to think of like finding order. Some people think of it as compression as well, finding the right compression, or minimizing entropy. You need to extract the order. So training a network to predict the next word is about understanding the order in language, understanding the structure. And you consume energy to create order in the network. You start with random weights, but then as you adjust it, it will become an ordered system. And it will dissipate a lot of heat. Those CPUs, GPUs, they will create a lot of heat, and then you will create order in nature in the form of a network. That is the same, that's the basic principle of life. A cell creates order inside the cell, and it produces a lot of waste. and we use the free energy that comes from the sun in order to do that. And the principle of life is essentially the principle of intelligence. And if we do understand the order, if we're extracting the patterns, then this model is not just going to be good at predicting the next word, but we expect it will be able to do many more things, as we'll soon see it doing. So when you predict the next word, what you can do is feed in that word again as an input, and you predict the next word, as you guys already did. And this process is essentially what we call autoregression. So you go back and you regress again. Once you've trained this network, and it will take a lot of energy to train, because these networks end up being with billions of parameters and so on, it will take a lot of energy to train them. And that's kind of fast-forwarding evolution, essentially, every time we train one of these models. Once we've trained, we can feed an input. We typically call this thing as a prompt, and then we can make a prediction. So here I'm going to use this language of prompt is what I'm going to, human types, for example, and then prediction is what the model produces. And I said a human types. It could actually be another model that types the prompt for the model, and as some people already do in some papers. But so in black, it's going to be what I'm going to type, and then the prediction of the network is going to be in blue. And if I do this, and I start introducing some structure, for example, I can type text, and I can type text in the form of a dialogue in black. That's the prompt. And then the model predicts a dialogue, a continuation of the dialogue. And if you have that, you now have a chatbot. That's all it takes. If you can predict the next word, and that, by the way, that's like for everyone here, especially here in Africa, that's the magic of machine learning. Step one is being really inventive about the data. It's knowing what data you could collect today to decide and how to do labeling automatically. So it was a genius move to think about, let's just take all the data on the web, and that's essentially what folks at OpenAI did with GPT-3, take all the data, all the text on the web, and just like predict the next word. And you always have the next word, so you have a label, so you have a supervised system. It's very easy to train just by minimizing cross-entropy, in other words, increasing order. And then this model will be able to do many other things because it has learned to extract the structure of language. And as we'll soon see, also the structure of videos or music or proteins and so on. And of course, once you have something that can predict the dialogue, you can just create a chatbot. It's just a question of creating the right UI for it, and you can talk to this thing. And it's incredibly useful. Like here in Africa, for example, say Nigeria, someone was showing me yesterday, the guys from Data Science Nigeria, that about 90% of the people have access to a phone with text. And if they do, that means you now can provide services to 90% of the population. And if, for example, things that provide education or expert advice, even on medical matters and so on, of course, with the right checks and safety in place. But the important thing is this opens up the possibility to, leveling, say, the field in terms of healthcare, banking, and so on. Here's a more interesting example. Instead of just having user and chatbot and then this dialogue, I add a third thing, which is, let's go to the web and get information. So let's do a search. So I type a link of where you could go to get information. And this was from the KIPO meeting, so it's all Montevideo. I have to do one for Ghana. And when it does that, the model actually predicts the right links where to go. And this is kind of cool, because even though here it's just imagining where it should go on the web, what it would expect the links to be, and the prediction is correct, it could actually go and click on the actual link. It could start using the browser. If you put the right UI to this thing, it now uses tools in the world to do better. And that's this tool use is actually really important. It's one of the most important aspects of intelligence. Um, to illustrate the structure that it learns, here's an example where this thing is called AlphaCore. The project, it was a project at Google DeepMind where you present a problem description from a code competition and you ask for it, the neural network to generate the code. And as you can see, this is the neural network here generating the code. It's amazing. It actually is a competitive programmer. And of course, this was sort of big news, got into the science journal. But my favorite take on this was from Scott Aronson, who has this great blog, Shtetl Optimized. And he mentioned this thing, that AlphaCode, it's like having a dog that speaks English, but everyone is complaining that the grammar isn't right. It's a super cool thing. We're making these huge inroads towards intelligence, and then we sort of start discarding it. Certainly in the last few years, I mean, I've studied this intelligence problem for 30 years, and the last few years have been just amazing. The things that we've been able to achieve really make me believe that the sort of intelligent machines is within our lifetimes for sure, and we need to be thinking seriously about it. Another example that I like about this is from Sebastian Bubeck of Microsoft Research, where his prompt is draw a unicorn in ticks. So it's a latex type setting. So that the network predicts the latex, and then you can compile the latex to a PDF, and it draws a picture. So it draws the unicorn, and this is what it did with ChatGPT. And then he did this cool thing that was, as GPT-4 was being trained, he would repeat this. And then during the process of learning, you can see that it sort of becomes better and better at drawing these unicorns. So it is actually learning some abstraction. I mean, this is not easy. Anyone who's tried ticks will know that ticks is incredibly hard, but the networks are able to do this well. And of course, the same networks, I'm going to go into the details of how this gets done, but exactly the same, pretty much the same network can be used to generate videos as well. So you can type a prompt, a white cat yawns loudly, and it will generate this video. This is with a Google thing called Funaki. There's also image and video. There's a few of these now. It's becoming common. I was involved in this work with some colleagues under the leadership of Scott Reed at DeepMind, where he took a big transformer as well, big neural network, and then all the data gets, whether it's images, whether it's proprioception, like for example, the little hairs in your ear are able to tell you how inclined your face is, and so on. So we have information about where our body is without perceiving it. So that gets also coded into the neural network. The actions, the motor control. And then, so what the team did is they took a lot of data for dialogues, for robots controlling things, doing tasks, for game playing, like Atari playing and so on, for captioning, taking an image and saying what the image is about in text. And they trained this model to be sort of a multitask model to do all these tasks. And they're actually able to succeed, which shows that it is possible to build these models, sort of general purpose models, and they're not just web models. They can actually be grounded. And by now, that is, over the last 2 years, there's been a series of publications where people have been using these sort of what we call these big neural networks, big language models or transformers to actually do robotics and to do all types of multimodal data. The same models, the transformer that we're going to go over today, are also used to take take a protein sequence and be able to determine its 3D structure. And of course, the 3D structure essentially gives you the mechanics of how this works. It gives you the functionality. Like here, we can see this animation of a pore, of a cell pore, which is just beautiful machine that we can engineer at a nanoscale now or that we can understand better. So there's been this huge revolution in biology. We have the InstaDeep folks here who've been much at the forefront of that, and bringing us closer to do things like last night I was having a conversation, and it's happening here with people from Africa designing vaccines to actually treat cancer, which is just amazing. It's like really well done. Back to the tool use. Language is a tool. So when we're training these machines to produce words and so on, they're essentially training them to use text to output to control tools. They can control browsers and so on. And when you use a tool, I think Daniel Dennett put this better, tool use is a dual side to intelligence, because a tool changes you. Once we acquired language, language starts changing how you think as well. And AutoGPT for those of you who know it, is a very good example of it, of how you can use language to change your actually thinking. And with it, come enormous opportunities. Because we will be able to, through this ability to generate words, to generate images, generate protein structure and so on, we'll be able to attack some really fundamental problems, whether it's bringing, I imagine one day everyone in the world will have access to a personalized tutor that will understand them, understand their context, and they will be able to learn any topic in their language. And the education will be tailored to their needs. And I think if we can level education in the world, we'll make enormous progress. And I think this is within reach. I think if we really set ourselves to do it, within 10 years we could do it. And of course, these models are very powerful. I'm not going to go much into it, but all sorts of questions will arise. There's ethical questions, there's safety questions, there's security questions. That are very important. I see there's a few sessions at Indaba that dealing with this, and I think those are really important. In a sense, some of the most fascinating problems that are left in AI are about that, are about how we control the technology well. Okay, so the transformer. I'm going to describe quickly the original version of it, which will match what's in the lab this afternoon. So if you're given a sequence of text, for example, in the form here of a question, then an encoder is just a neural network. And I'm going to give you now the abstract view, and then we're going to zoom in and look at what exactly is inside this encoder. But it will be a transformation where a word will be transformed to a vector. So that's what I'm showing there. I'm showing 5 vectors with 4 entries. And then the encoder is just a mapping. Just think of it like a bunch of matrix multiplications and nonlinear functions and so on. And then it will produce vectors of the same size and in the same number. Those vectors will go into a second neural network that we will call the decoder. And the decoder will also have as a starter a token that we will just going to call the start of a sentence, the start of a prediction. So the question here is the prompt, essentially. And now we're going to start generating the predictions. So it autoregressively, predicts the word me, you feed it in, predict the next one, me or yeah. Drilling down, this is the original architecture for Transformer of 2017 by Vaswani and colleagues. And what I'm going to do next is go into each of these components. So essentially, a transformer is just a transformation. There's nonlinear transformation of the input into an output. So it will take a sentence and it will predict the probability of what the next word should be. And you have a finite vocabulary. So for example, maybe you only have 300,000 possible next words. And so it will predict 300,000 probabilities that sum to 1. So what's the probability of each possible word coming next? The first thing you do is encode the input, the text as an input. And so as is illustrated here, and I took this example from Lucas Bayer, you first have an input sentence, like in this case the prompt is, the detective investigated. The first thing we do is we split that sentence into chunks. So I mentioned we do words, but it's more effective if you do a clustering, and instead of words, we use pieces. And typically, if you go to GitHub, you look for the sentence piece tokenizer, and it will explain how this is done. Once you break the sentence into these segments, then each segment is given an ID. There's a finite number of these, and so these sort of are represented with integers. Here the integers 3, 721, 68, and so on. And so we call this this basically a tokenizer. So we have tokens, we have token indices, integers, and the token integers point. If you know the index, you know exactly which word to insert. And typically this, I'm going over this detail because if you go to GitHub and look at the code for a transformer, this is how you'll see the implementation. And there is also a vector that we feed as input. I'm not going to go into detail into what that vector does, but it essentially just tells you what is the position in the sentence of the word. And people have devised different ways of doing this. One thing that's very important to understand is the concept of attention. So you've probably heard that attention is all you need. It may not even be necessary, some say, but it's definitely the thing that is used the most right now. So it's important to understand. It's one of the most important operations to understand neural networks. So the encoder will produce, as I mentioned, will produce a bunch of vectors. So if the input sentence was, where are you? And let's assume that it's 3 tokens. So the encoder will produce 3 vectors corresponding to each of these 3 tokens. And then you get to choose the dimensionality of those vectors. That's one of the design options you have. So in this case, it's about, 6. And as you start making a prediction, like in this case, where are you in Uruguay? Then that prediction that you're generating and you're feeding in autoregressively, in this case, has 2 tokens. And so we want the decoder to produce 2 tokens. So that's the setup for multi-head attention. So it's a module that takes in 2 things. It takes in the output of the encoder. It takes on its own input, and it will produce something that has the same size as its own input. The operation is as follows. So let's assume here we have dimensionality 6, and we have 3 tokens as that we're going to cross-attend to. So that's what people call cross-attention. We're going to cross-attend to these M tokens using the X tokens. The first step is we introduce matrices of parameters, P, and we give them names, P query, P key, and P value, and we project them into vectors, into matrices that we call the keys, the queries, and the values. And the idea here is a concept from databases. You have a query. With the query, if a query is similar to a key, you read the value that is indexed by the key. So this is a way of accessing information. So using the output, as you're making predictions, you keep accessing the input to pull information out of the input. And so the first thing we do after we have these 3 quantities is we find a similarity between the query and the keys. So we basically find out where we're going to seek information. Once we have, and so basically for the N, for the 2 orange things, we're going to compare them to every blue vector to see where to extract information out of the blue vectors. And then what we do is we do the softmax, which is just, we have a matrix that is n by m, number of our tokens in the decoder times number of tokens in the encoder. And then we're going to, so that's a matrix. We take each row, we normalize it so that it sums to 1. Because then we're going to do a probabilistic read. So we're going to look, if something is very probable to be similar to the query, and you do the dot product of query keys, then you're going to read it. So we not just read one item from the database, but we read several items. And then we introduce parameters to normalize it on the way out, so we get as the output the normal vectors. This is all of attention. These are all the, it's just with time you can sit down, you can check the matrix dimensions, and this is all the operations that need to be done in order to do cross-attention. There's another thing at the input called self-attention. So just you can, instead of having M that attend to, you can attend to yourself. So you can sort of build a model how the data, I mean, for say a pixel in an image can look at its neighboring pixels to sort of decide how it's going to transform itself. So then you can get these image transformations or text transformations. So in self-attention, there's only access, but the operations are exactly the same. The only thing with self-attention is we're feeding in Uruguay at the input, and then we also have that as the output of the decoder. So we need to make sure that when you're making a prediction, that prediction doesn't cheat by, because it knows the answer, looking into the future. So in the softmax, we're going to add a mask so that you can't look into the future. And the mask is just a way of, as I show here, so if you have this matrix, and this is the matrix that is, if the output had predicted so far, I am fine. Suppose on the rows you're at the word am, so the word am should not look at a word in the future, which is fine. And so what we do is we need to get rid of all those entries in the matrix, in the weight matrix. We need to get rid of those entries in the upper diagonal. And the way this is done is very simple. You can just add another matrix to your existing matrix, which has minus infinities and zeros. And then when you exponentiate that through the softmax, which is as you exponentiate and normalize, it will zero out the entries. And so your network then is autoregressive. It doesn't cheat, doesn't look into the future. When you're making a prediction, you only look at the past. So actually, let's make this a bit interactive. Why would we have to do all this work to try to make the model, instead of going one word, predicting one word, training one by one, why would we want to introduce this matrix, this mask? Anyone? Why would we want to present the full sentence and not just go one by one? To speed it up. Because if you can present the full sentence, you can process all this in parallel. You don't need to go one prediction and then do again another prediction. No, you just pass all the predictions in parallel. So it's full matrix multiplication. The one thing about the transformer is an extremely efficient. It was engineered to be efficient. That's the ideas of attention and so on, all the ideas in this architecture are old ideas. But the thinking that goes into making this really efficient is actually really what made it so popular. Because by making it really efficient, the researchers at Google could scale it up. And that also enabled OpenAI folks to then scale it up even further. And now there's a race by everyone to make the networks bigger and bigger. I'm not going to go much more into these other details. You're going to see this in the lab. But another thing that you can do, you take the keys, the queries, and the values, and you can say, for example, split them in half, and then you do the operations in parallel. You do, you split them in half, and so half of them you do one attention, and then the other half you do another attention. These things are called attention heads, as this illustration shows. And so you can also split them in thirds, and then you have 3 heads. And then for each head, you compute a prediction, And then you combine the predictions with a weight to generate an output vector that has, again, the same dimension. So this can be thought as a factorization that, again, makes things much more computationally efficient. And for those who are familiar with RBFs and traditional machine learning, you'll see that this is just again, taking a linear combination of basis functions to produce the output. And so this thing is called multi-head attention. It's very popular. And this is the code for a transformer. So I took this from a tutorial by Noam Shazir. I think it's titled "One Right Head is All You Need," which is one of the best papers explaining this, highly recommended. And as you can see, you have the matrices of parameters, PQ, PK, PV, and PO. Another thing that we're going to do is when we process sequences to sequence, instead of doing one sequence at a time, we use a batch of several sequences. So you introduce this new dimension, the batch dimension, for all your data. So now X is not only n by d, but it also has a batch. M also has a batch. And then if we have heads, K is usually D divided by the number of heads. It's usually automatic. And so these are your matrices. This is your input. And then this is actually code. That's not a comment. That's actually code using TensorFlow and some. We have JAX as well does this. So the query is just X times the parameters. And this will make sure that you have the right dimensions. So it's exactly the math we looked at. So the code just matches perfectly the graphs and that we saw. You compute the logits, which is the similarity between the queries and the keys. And then based on the similarity, so we add the mask, we normalize so that that matrix has rows that sum to 1. And of course, by adding the mask, we get rid of the future, so we make sure that no token looks at the future. Everything is done efficiently with these large matrices or tensors, hence TensorFlow. And then we do the read. So given the weights, the read is you use the weights to decide which values you extract, which information you read. So you take a linear combination of the information to produce the output. And then you just normalize it. Again, you use parameters to get something that it has so that Y has the same dimension as X. And that's attention. And that's like the thing that's pretty much used everywhere. There's some modifications that are quite popular. So like one, for example, is this thing here where you, for the keys and the values, you don't use heads. You only use heads for the queries. So you can have, basically you can have multiple queries to the same data as opposed to a single query to the data. And folks do this just to get much more efficient inference. This is a very useful trick to speed up inference. Okay, so that's attention. But that's not a transform. A transform is actually the sequence of operations, which involves self-attention, and then I'm going to go into what the normalization is, the feed-forward, and so on. You put all these things together, and we call that thing a block. It's in itself, it's kind of like Lego. Each of these components is like a Lego piece. You build something out of Lego that's bigger, and that thing of Lego is in itself a component that you can glue together. And usually you repeat these operations, say, n times. So you do the whole transformer block n times. Transformer blocks are, again, one of the big innovations is sort of trying to come up with the right operations there. The feed-forward is a standard thing. It's just like an old neural network where you take an input, multiply it by, as the equation shows there, by a matrix of parameters. You sort of expand it by a certain factor. You then pass it through a nonlinearity. Here is Jello, which is just something like that looks kind of like this. And out comes a vector. And actually, when you do this there's a lot of parameters in these things, in this module. And a lot of the memories that the networks have are encoded in these parameters. The other common component is normalization. So to make sure that the optimization doesn't blow up and so on, we have to take all the activations, sum them, and divide by the sum to keep it normalized. There's different ways of doing this. Layer norm is one, then there's like all sorts of RMS norm, all sorts of ways of normalizing. In the original transformer, folks were doing and of course there's another thing that is used a lot here is these sort of skip connections. This comes from something called ResNet, and the idea is you add, like the equation shows here, to produce an output, you add the input to the transformation that the signal went through the normalization. And the original transformers, they tended to do first the normalization and then add things. First you pass it through the module and then you normalize, like it's in this picture. But these days we do it differently. I'll show an example of that next. Finally, you sort of use just a matrix multiplication to bring things down to the right dimensionality, the word vocabulary, and then you predict the probability of each next word. And that's how we do it. That's the encoder decoder. That's what we used to do the code thing, alpha code. The family of models, T5 models that you can get on GitHub, Google models, they also have this type of architecture. There is a different way of processing the data. That's a different architecture. It's called BERT, different way of training. So instead of predicting the next character, what you do is you mask some of the input. So you hide some of the words, and you try to use the network to predict the words that are missing. And meaning is a lot about context. The meaning of something depends on the context. And so using the context, these networks, which the words that come with it, the networks learn to predict that word. So that's one way of training. And another way to predict the next word, like in this case, you have a start sentence and then the cat, and then the prediction is sat. It doesn't use an encoder-decoder, but it only uses one network. And this is what the family of GPT models do, GPT-3, 4, and so on. And it's also, if you go to look at the DeepMind Haiku library, the language model that's described there, and this is actually the code from the Haiku library, has a slightly different architecture. So as I just mentioned before, instead of doing the layer normalization after, you do it before. And that, of course, involved a lot of experimentation and so on to figure this out. It still uses the attention dropout. That's a regularization technique. It's a randomization that stabilizes training and gives you, it prevents feature conduct. It creates better features. And so on. And then you do similar operations as before. You again have a feed forward. So this type of model, and again, the code these days, if you use something like Haiku, or you'll see that you create an annotation block, and you essentially, these days, the code will give you all these things. They will give you what the layer norm is, it will give you the normalization, you apply attention, you do dropout. This is the residual connection where you add input to the transformed signal. And then you do this sort of sequential, this feed-forward block, and so on. So if you go look at the code, it matches very well what these pictures do. And then, of course, there's all the other code that is about the configs, how to load the data, and so on. And that you get to play a bit with during the collab today. All right, so that's going into detail. And I'm now going to quickly come out of the detail, and I'm going to show you a bunch more applications of transformers. So we're going to now like zoom out to see what else you can do. So one of the things first you can do is not just do text, but you can take an image, you can break the image into small patches and project them into small vectors. And now you can treat those vectors as, at the position of the patch in the image, and use this, use a transformer to actually predict, just like before, like whether an image is about a cat or a dog or, I don't know, a landscape. And so that's usually called the vision transformers, or VITs. In order to get the equivalent tokenizers, so for words we have these tokenizers, and words are already discrete. For images, one popular technique for getting tokens is VQVAEs. So a VQVAE is something that, it's a neural net technique that takes as input an image and uses a convnet to generate a bunch of responses. And then what it does is for each of the neuron outputs, it maintains a library, a finite library of vectors. It looks for the nearest neighbor here, and the nearest neighbor is what gets passed to then invert this operation to generate the image. So you basically need to predict the same image as the input. So then the training, we know what we're training for. There's a concrete objective. And then the way these vectors get updated is every time a vector is selected, you keep that in memory, and then you just average all the input vectors that were the nearest neighbor to this guy. So you just do an averaging of every time all the vectors here that are matched with a vector. And so essentially we're quantizing or discretizing the image. So there'll be a finite, usually you pass a convnet, you get these vectors out of the convnet, or this could actually be a transformer as well. And then out of these vectors, then here we just get a finite vocabulary. It's a popular way of doing it. I'm not sure that even that you need to kind of do it this way. There's many ways in which you could try to get a finite vocabulary. I'm going to skip this. It's in Mr. Murphy there, book. He explains this in great detail. Actually, this is a cut and paste from his book. And the reason why I was explaining this is because this gets used a lot. In machine learning, there's lots of papers, but there's very few ideas. I've said this before and I repeat it. There's very few ideas. If you learn VQVAEs and if you learn transformers and attention and so on, you can pretty much understand all papers because it's just a rehash of the same ideas. There's one Google paper called Partai, and what they do there is essentially use these ideas. It's like playing Lego, really. Once you know the basic pieces of Lego, you just keep using them over and over and over again, and you can write thousands of papers with that. So you use a VQVAE to get tokens. Once you have tokens, those tokens are just vectors. So you can start by using one bit of the image. For a new image, you have a start token, and then you predict what the first patch of the image should be. Once you have that first patch, you feed it in autoregressively, you predict the next patch, and so on. So you can now generate an image in the same way as we generate text. And you can make it conditional on text, like with this encoder-decoder architecture used in Partai. So you can do things like draw a picture of a cat, and so on. And these are things that's pretty much a solved problem these days. We make the models larger, and you can generate any image. So there's lots of approaches now that do this routinely available. So these models are able to compress the statistics of all the possible images we see in the world. And it's just a remarkable fact. I never, the images 10 years ago were like sort of clouds and stuff. We never thought we could do this. I worked on this a lot and just never imagined one day I would be looking at these results. It's just been so transformative what has happened. And by the way, this idea of generating, whether it's generating text or images or video or structures or generating any media, The principle is always, in terms of learning, is you generate something, you compare to what it should have been. And that's, again, another way to think of how intelligence works. You're always, if what you imagine doesn't match what you see, you have to learn. If your hand, the brain's always predicting what's going to come next. As my hand is approaching this object, I can already imagine what it's going to feel. And if I touch it, and it's like, oh my God, it's 50 degrees. I wouldn't expect, you wouldn't expect this to be 50 degrees. You always make, and then you correct. You quickly learn, oh my God, I'm touching a stove. But most of the predictions is just confirmations. Occasionally you get surprise. Okay, and surprise just means, it can just be measured in terms of perplexity or uncertainty. And if you get surprise, you need to create more order. So you consume energy out of the power grid, dissipate heat, according to the law or second law of thermodynamics, and you create structure and you learn. Folks have also tried to, instead of going out regressively like we were doing, just going bit by bit over the image, folks have tried to also generate the whole image in parallel. And there's a very nice technique that I quite like, is mask it. And this is what they do. So they use, again, same reuse of ideas. They use a VQVAE to create these visual tokens. And so here represented with colors, but this is just like an integer that indicates which vector gets coded, the patch gets coded to. And then they train a second transformer. They call it a bidirectional transformer, but it's essentially the second architecture I mentioned. It's like BERT, where you mask some of the input tokens, and then you try to denoise them. You try to predict using the context. Because just like, again, meaning is about context. Just like in language, the words around you sort of predict what word you should be. In images, the pixels around you sort of predict what pixel you should be. And so they train this transformer, and then they're able to, instead of generating images sequentially like the top, like folks used to do it, they can sort of create them bit by bit. They can come up with a schedule where you sort of unmask the image. And one way to think about it is you undo this noise, this discrete noise that is just blanking out the image. So it's much faster, much more efficient. And folks have used this to do video generation. So in particular, there is this paper called Fenaki that again uses the same things. It uses something like a VQVAE tokenizer. So that's the first stage. It's called a C-Vivid encoder because it actually uses a VIT encoder. It does space and time, uses a space and time transformer. So instead of trying to do the video is very big. So instead of processing the whole video in one go, you kind of do, you first process it in space, then you process it in time. So you factorize to make it more efficient. That's just, whoops, that's a detail. And of course, and they do these sort of tricks where instead of processing one image at a time, they sort of quantize, say, 2 frames together. So that's the first stage. So they train this as a VQVAE that has, instead of convnets, it has, actually also has, it uses transformers. And then the next stage, what they do is, having trained these things, having trained the VQVAE, they then plug it here to generate, to tokenize the video. So all this is about creating tokens. So you use something to create tokens. Once you have tokens, you can now take one of these language models that was pre-trained, a T5 model, to encode text. So if you want to generate a video about, say, a cat yawning, you would write the text here. And when you train, you pass in the video. And then you mask, you do the sort of the mask it trick again. You delete some of the stuff, and then you train a transformer. What's trained here is this transformer that unmasks. So you learn to unmask. Once you have a transformer that can unmask, you take it here, you put it here, and now you start from 0, and you generate the first few frames of a video. You then condition on those first few frames autoregressively, and you generate the next block of frames. And if you now want to generate a long movie, this could be one sentence, this could be the next sentence in the script, and they do this, they generate these sort of 2-minute long movies as they go through the paragraph, sentence by sentence, and then they can create long movies. Just to give you some examples, this is the cat yawning that gets generated automatically. Within 5 years, we will be able to, there will be several different, oh, sorry, there's a question there. Go ahead. And by the way, I should have said that I would love some questions. We have plenty of time. We've still got about 10 minutes for questions.
Hi, this is Daniela from South Africa. I'm interested in how we evaluate these image and video generative tools. Like the step change in the generation capabilities has been amazing. And I'm interested to hear how the ways that we evaluate is changing as well. Like how do we evaluate whether a generated video is good or bad without necessarily just comparing to like the original pixels we have in the training image. So yeah, I don't know if you can say anything about the metrics that we're using to kind of evaluate fidelity and quality of these images.
Yeah, so, I mean, the first, that's a great question. So, and there isn't a straightforward answer. I mean, you can use likelihood, just the perplexity, as that would be the first thing to kind of predict whether you kind of, if a model has higher likelihood, it will likely generate better the data, because that's what we trained it for. But then folks have also come up with different perceptual measures, you know, that they borrow sort of from the compression, literature, FID, and so on. And those also give us some guidelines of how well the models are, but they're also not perfect. And then comes the ultimate thing, is which you eye them, and you check if it makes sense, and you sort of maintain a history of like what things you were generating. With video, I think one thing that's sort of becoming, I think, possible as well is like you can use like simulation of like realistic physics where you actually know state and so on, and you can actually now go and try to estimate, measure whether, say, the video is physically, realistically, or plausible. You can use networks. And I think this is one of the most important ideas actually in this that I hadn't mentioned is if you can train a network to, for example, go from images, a transformer that goes from images to text, and you can use it as a detector, as a success detector of correctness. So you have an evaluation function. So transformers can be used as the model itself can be used to reevaluate the model or other models. And so with that evaluation, if you, for example, asked to generate a cat, but then your network says you haven't generated a cat, you can use that as a measure of performance. I think in the future, more and more, we're going to see this type of automatic evaluation. We already see this with language models, whether you can ask a language model to generate some text, and then you can ask a language model to ask, is the text generated, accurate? And, this model could maybe query Wikipedia to check. That's a really interesting part of research, this sort of very automatic verification. But it's natural that that's where we're going to go. Because we're always also, humans do this, we're always checking in our head whether what we're saying makes sense. Yeah, there's a gap between stimulus and response, and there lies our freedom, I think is the quote. One more?
Hi, Nando. Maria from South Africa. Thanks for the very clear introduction. I have a question about the embedding, especially in the very simple vanilla architecture. So it seems like the first time that text enters the realm of numerical analysis, so where the features become numbers, is actually right at the beginning when we make vectors. So when token IDs become vectors. And my question will be how sensitive basically the performance of the rest of the architecture is towards this step, or phrased in a different way, if this architecture demands things from this step, for example, that there has to be a certain compression or decisions made, or maybe another way yet to phrase it is if there's already a feature modulation or extraction happening at that step, or if it's basically just do whatever you want in this step, we will extract the features later anyways, as long as it's not too stupid.
No, thanks for the question. It does matter what you do there. And because if I think of position encoding, like every year there's a new paper on how to do position encodings. I think the rotary embeddings is the latest. So that transformation does impact performance. It's clear, at least, if you look at positional embeddings. And yeah, if you just put in any, so those embeddings are trained, just back. I mean, I forgot to mention this, but you take the signal, feed it to the output, and then train the whole thing by backprobe. But if you take from an existing architecture and just plug them in, there might be changes in performance. How much, I don't know. But it's certainly, at least at the position embeddings, it's clear that different people have different papers. Kevin might know. Kevin, can you use the microphone?
I don't know the answer, but I have a question, but it's related. So let's suppose the vocabulary size is 30,000 words, and you can represent that, as one hot. Do people embed into a 30,000 dimensional space or a 300,000 dimensional space? Is it expansive or contractive? And could you just use a random matrix there and with bounded norm or something? Or is it important that it's trained? I mean, this is just further elaborating on Mary's question.
Yeah, I don't know. I mean, you could do definitely randomize, and it probably train it, we could still recover that. So I suspect it could still work. The question is how well. Yeah, I don't know the exact results you would get in an experiment. It will depend on the scale, the data set, and so on, the rest of the network. Usually when you train these, there's tons of hyperparameters and decisions.
Yeah, there must be LLM experts in the audience. Is it expansive? 10x bigger? Anyone? I guess the experts don't come to this.
Well, in the lab this afternoon, you can actually do that experiment, and then you can actually calculate.
There we go.
We can do this with pen and paper offline.
Thank you.
All right, I'm going to wrap up. So there's one more question. I still have about, I'm almost done at the end.
Thanks for the great introduction, Nando. So my question is, especially in production, one of the most difficult aspects of dealing with these autoregressive language models is that you can't control the outputs completely, so there is an element of randomness. And in some use cases, you really want to control that, right? So like in education, you don't want the model to say something that's wrong, right? Verification is very, very important. So you already mentioned that you could potentially use another language model to verify, right? I'm wondering what other kind of intuitions you have around how that problem will be solved. So basically to verify and constrain stochastic outputs.
Yeah, so there's many ways. So you probably have heard of constitution AI and using multiple reward functions and so on, RLHF, topics that I'm not covering here. But folks have come up with, for example, you use different reward functions and you get an output and you score it according to a reward function. So the simplest thing is if you have reward functions for things being accurate and truthful and not being offensive, etc., then you can make several predictions. Instead of just one, you sample several. So, and then you score each of them. You can rank them. Usually this requires that you use either other model or a human in the loop annotators to rank them. You take the top 3 in the rank, and then you retrain the model with the top 3. So basically what I've described is RLHF, or policy gradients from data. And doing this, you can sort of you can force the model to act in particular ways. Often when you do that, it's still a research question of how much of the original learnings you break, how much of the original structural order you break. Actually, I'm going to move on, finish, and then we'll just finish with some questions before we all go for the picture outside. I've already gone over this. I'm not going to go into the details of Gato, but it's the same idea of tokenizing. Finally, there's another idea. I'm basically covering what I think is all the ideas that you need to know all of the papers that come out. So if you know VKVA's transformers annotation, and you know this other thing called diffusion and mask-it, diffusion is kind of like mask-it, but instead of unmasking by flipping patches, we're going to do that with Gaussian noise. And if you know these ideas, you pretty much can read any paper. Very quickly, crash course on diffusion. If you start with an image and you add Gaussian noise to it in small steps, very quickly becomes noise. This is a property of Gaussians. At the geometrically fast speed, things become noise. It very rapidly becomes noise. You can do then the opposite, which is you can start at noise. So now you've got basically a sequence. Now you can train a network, and you do this inside a probability, but you train a network to undo the noise. And the same network should undo the noise at each stage. And that's essentially diffusion. The rest is Bayes' rule and a bit of math, and for the details, once again, go to Kevin Murphy's book. The network that you use in each of these stages is one that I saw a lot in the slides yesterday, sorry, in the poster sessions. It's something called a U-net. It's sort of shaped as a U. And you could do this with convnets or with transformers. The typical one that I'm showing here is with a convnet, whoops, where you have several, wrong button. You do several applications of convolutional nets. The convolutional net's another one you need to know. That's also a cornerstone. You copy these activations to the output. You do a projection to a lower dimensional space, and that projection is using techniques from convnets, pooling, but you could also use compression. You could use wavelets and so on to compress this. And you keep going down to the U, and you keep repeating this operation of copying. And so essentially what you're doing is you're doing a multi-resolution, high resolution, low resolution transformation of the image. So this U-net is learning to do an image-to-image transformation that undoes the noise, and it tries to do it at all possible resolutions. It's one of the coolest ideas in machine learning, this U-net. You can also sort of, at the bottom here, use a transformer, and folks try to do this very quickly with wavelets, put a transformer, like Tim Salamans and colleagues have a beautiful paper where they do this. They put a transformer here, because it can be done, again, the transformer can be done really efficiently in our parallel GPUs and TPUs. And then you bring it back to the top. That's called a U-VIT, U-shaped vision transformer. And then I can now describe something called stable diffusion, which to me exemplifies really what machine learning is about these days, Lego. Because to get their approach, which allows them to generate images conditioned on text, and it's very popular, what they do is basically they reuse VQVAEs. So step one in the red box is they train a VQVAE, so they're able to take an image and code it to a lower dimensional space. If it's lower dimensional, they can use cheaper computers to basically do the diffusion. The diffusion then gets done in this lower dimensional space, and then their UNet needs to attend to the text. Like, for example, if you say an image of a cat, they use a existing transformer, like say a T5 or something like that, to take the text, produce an embedding. These are embeddings here. These embeddings can cross-attend to this embedding. So the image can look at the text to decide which pixel should come next. And then so each step is basically, again, a transformer. So the transformer really isn't everything. This concept of attention, if you kind of, I mean, this basically summarizes it. You need to know how to use a transformer to encode text, UNets, VKVAEs, and then this process of denoising, which is like mask it, or like BERT, or like diffusion. And it's pretty much the same ideas over and over again. And it's all about how to play nicely with the Lego pieces. Okay, I'm going to skip this. This is sort of detail. Here's some of nice images. And I'm going to wrap up here because we have our picture coming up. I think we have time for a couple of questions. Let me check with the organizers. Yeah? And we have one over there. The lady here in front. Light blue. Oh, right here. While we get the microphone there, again, an ad for go do the collab, because the collab goes exactly through what I've covered here. And it does a bit more. It actually tells you how to fine-tune transformers, and it introduced some really cool idea called LoRa, for low-rank adaptation, which I think everyone should learn.
Hey, now I know that transformers can work with images and text, but I want to know if I can use it with time series data like EEG or event data.
Yes, you could. So,
How?
for example, speech, which is a time series, is one where these models are used a lot as well. So, in fact, I was doing text-to-text sequences, but there's nothing that says, and I was using tokens to tokens, but there's nothing that says you couldn't do speech-to-speech. In fact, that's how we're doing video-to-video. Video is a sequence, and you could do it for any sequences, EEG, ECG, the tactile sensing of a robot, if you have it, because this basically is like eyes. A hand can sort of see the world. So you could use really any sequence, and
I will group the sequence into chunks, then enter it to the transformers. This is how it's done.
Sorry, I couldn't hear the last bit.
I would crop the sequence into several chunks and enter them to the transformers, or the technique.
That's correct. So you would try to, for example, if you have a time series, you could try to project it, maybe take small patches of it and try to come up with some code book, some discretization. So you figure out some way of tokenizing it.
Okay, great.
Another thing you could do, if you have speech or music, there's a technique called refusion that does this. You could also find a spectrogram, which is an image.
Yes, yes.
And then basically the time series becomes an image to image to image. So you use the same. But like with the Gato thing, what we're trying to do is like any signal. Look, at the end of the day, whether it's images or sequences of nucleotides or anything you can put on a laptop, is essentially a sequence of ones and zeros. You can train a transformer with a sequence of ones and zeros, so you can do any data.
Great.
It's
Thank
a
you.
universal machine. There's one right here in front.
Okay, thank you so much for the talk. I've really learned a lot. I have a question, but it's not quite directly linked to what you presented. So we call them transformers because they are trying to transform the, let's say, in terms of text, the mass of knowledge that we accumulated, and trying to piece that together to provide new, maybe new text, new knowledge. So the question I have, is it possible to somehow determine which data is actually meaningful? So let's say in terms of Google, you know, let's say it's collected so much knowledge over the years. A lot of it is replicated information or duplication. So, you know, we talk about biases in the models and kind of reinforcing specific things. Is it possible somehow through maybe some of the techniques you've shown to determine how much of what we've collected is actually meaningful regarding the results that we are getting?
That's actually a brilliant question, and one of the greatest questions now of our times in AI, which is the question of provenance. And I think it's context. Whenever you generate something, what contributed to generate that? I think, if I understand well, that would be a paraphrasing of it. What out of all the data that one used, say the web, or I don't know, YouTube, or whatever your data is, what was the data that contributed to this creation? And that's important first because of copyright. If you're generating, you know, recipes in the style of, I don't know, actually someone mentioned this to me, Yota Motolenge, who's a chef, then you kind of then want to give some attribution to maybe that person. So questions of royalties, business models around this are fairly open at present. We don't have good techniques to be able to tell, given a prediction, exactly what data led to that prediction. I mean, you can do sort of a nearest neighbor search. Like if you generate an essay, you can do I guess a search over all your data to find the nearest neighbor and maybe say which things are responsible for it. But that's still somewhat unsatisfactory as well as expensive. It is an open question, and it's a really important one. Because if, you know, especially if you use a lot of movies to generate a new movie, then who should you credit? You know, artists deal with this problem all the time, where there is innovative art, but then art sort of builds also on the past. We reuse elements of the past. We build on the previous generations of artists. But we have to give credit. And this question is kind of how to do that properly. It's an open question. It's a great research question, by the way. For anyone here, it's like, what training data does this current prediction depend on? Thank you.
Hi, I have another question. So it seems that we as a field are kind of moving in this direction of foundation models, this small number of models that do everything, kind of moving away from these fine-tuned versions or having individual models for different things. So I wanted to get your thoughts on whether you think this is a good thing, you know, if there are any risks in this, or if we might be missing out on some things by going down this path.
Yeah, fortunately, there's people exploring other models. And there could be that a new idea will come and will knock this. But some of these ideas are quite stable. Like the conf block, for example, it comes from the 70s. And it's based actually in the Hubble-Wiesel model. Actually, I once spoke to Professor Fukushima, who invented the new cognitron, which is the architecture of the ConvNet. And he said he was inspired by Hubble and Wiesel. He was working in a multidisciplinary lab in Japan, and then by chance had neuroscience next to him, and that's how he learned about it, and then he went and he coded it. And then Jan LeCun later added backpropagation to it. And that block has stayed with us since the 70s. And attention was a block earlier that sort of stayed with us. Normalization has stayed with us for decades. So the Lego pieces are somewhat stay with us. But I believe there's a lot of Lego pieces that we could still invent. And some of them will be more efficient, for example, for inference. One thing, on the one hand, training this model is expensive because, like I said, we're not just learning the lifetime of an individual. We're actually learning all of human evolution, all of culture, the whole web, all the libraries, all in one training session. And evolution was expensive. So you kind of really consume a lot of energy. But I would still hope that we come up with much more efficient architectures in terms of energy consumption. And certainly at inference time, like for example, our brains are like 90-something% sparse. Our models are very dense. And very much the transformers and architecture is beautifully designed for the current hardware. Potentially we might have different hardware in the future that will allow us to implement much more efficient machines. So there's still, we haven't converged. We have some good Lego pieces, but the game isn't over in terms of inventing new Lego, new machines, new hardware. Thank you.
Thanks so much, Nando. If we could all make our way outside to the BOM library for the group photo, please.